In this video, I'm going to discuss function notation. Now, function notation is simply a method of writing algebraic variables as functions of other variables. So in this first example, it looks like we have y equals 3x plus 5, and this is an equation. It has two variables, y and x, and typically when we see things like this, x is going to be our independent variable, and y is going to be our dependent variable. And we consider this to be an explicit form since y is by itself and is explicitly solved for. So to be in function notation, we're going to take this y and we're going to exchange it for f of x. And my right side is going to stay the same. So we're going to say f of x equals 3x plus 5, where x is still my independent variable. And now, instead of having y as my dependent variable, I kind of have this f of x, or whatever this expression turns out to be whenever I substitute value for x, that's going to be my dependent variable. Okay, so we can write this a couple of ways when we're actually finding some values. So if we have f of 2, that means that 2 got substituted for x right here, which means we're also going to substitute for x right there. So it's going to end up being 3 and then times the 2 plus 5. So 3 times 2 is 6 plus 5 equals 11. So 2 was my independent variable, and 11 is my dependent variable, or my actual value that I got once I substituted that independent variable in. So as far as an ordered pair, we can say we plugged in 2, my independent variable, for x, and I got 11 out. So I can say my ordered pair is 2, 11. Likewise, we can use the same function and substitute other values in. Let's say we have f of negative 3 means that we're going to substitute negative 3 in for our value of x. So 3 times negative 3 and then plus 5 will be negative 9 plus 5 equals negative 4. So as an ordered pair, x was negative 3, my independent variable, and I got negative 4 from my expression when I simplified it. So we kind of have this function here, and this function definition is f of x, which f names the function, and x here tells the independent variable, and it equals 3x plus 5. So anytime we want to substitute a value for our independent variable, or for our x, we place it here, saying that we're going to replace it for x, and then we replace it with x over here as well, just like we've been doing. Another example is that we have y equals 3 minus x squared. And again, this is in explicit form since y is all by itself. So we can simply exchange the y for f of x and then complete the right side of the equation with what we had before. So now in our function notation we have f of x equals 3 minus x squared. So this is nice because, again, as we did in the previous example, we can substitute values for x. So let's say we're going to find f of 3. So that means we're going to put 3 minus and then substitute 3 in for the x. So 3, and that gets squared. So it's going to be 3 minus 9, which equals negative 6. So as an ordered pair, we can say my x value, or my independent variable, was 3, and my y value, or dependent variable, was negative 6. Okay, so I can do another one. Let's say f of negative 4, which just means, again, I'm going to substitute negative 4 in for my x. So 3 minus negative 4 squared. And recall that when you substitute values, you're going to always put them in parentheses. So this ends up being 3 minus, and this right here will end up being a positive 16. So just 3 minus 16 will equal negative 13. And again, as an ordered pair, my independent variable, or my x, was negative 4. And what I got when I simplified it was negative 13, which I could call my y, or my dependent variable. In this final example, we can see that an equation in explicit form has already been put in function notation. So we have f of x equals x squared minus 2x plus 1. Okay, so we can find a couple of values here. We could say f of 1 equals, and then just go ahead and substitute 1 in. So 1 squared minus 2 times 1 plus 1. It's going to be 1 minus 2 plus 1, which 1 minus 2 is negative 1, Negative 1 plus 1 equals 0. So we could write this as an ordered pair and say 1, 0 once we put our independent variable of x in and we receive 0 as the dependent variable. Okay, or we could set up a table of values. We could say x, and then normally we would say y, but in this case I'm going to say f of x, and we can set up a nice table. So I already know that I got 1 to be 0. So let's also plug 0 in, and negative 1, and maybe 2 and 3, just to kind of get an idea what's going on here. So when I plug negative 1 in, it's going to be negative 1. So we can say f of negative 1 equals negative 1 squared minus 2 times negative 1, and then plus 1. So 1 plus 2 plus 1, and that makes a nice 4 right there. So when I plugged in negative 1, I got 4. F of 0, zeros are always nice because anything with a variable is just going to go away. So 0 squared makes 0, minus 2 times 0 gives you 0. So it ends up just being 1. So we can put a 1 right there. Also, we could find f of 2, and it's going to be 2 squared minus 2 times 2 plus 1. So 4 minus 4 plus 1 is just going to be 1 again. And that's pretty nice. And finally, let's go f of 3. So we can have 3 squared minus 2 times 3 plus 1. So 9 minus 6 plus 1 should be 9 minus 6 should be 3, plus 1 is 4. So actually this makes some nice patterns simply because I know this function is going to be a nice parabola. It's quadratic in nature, which is far beyond the scope of this video. So our function notation is f of x equals and then some expression, and we can easily substitute values into that expression to find values, make ordered pairs out of them, or even complete big tables, so later we can graph some stuff. But this video is function notation, and there you go.